Hello everyone, we're ready to start. The menu for today, we'll finish congestion control. Tomorrow tests, number 5, lab 5 will start. And this is the last week of the course evaluation. Don't forget to fill in the course evaluation, even if you like the course. And we were told that the participation in computer science in the past years was particularly low, which is paradoxical for people who are supposed to be in love with computers and online stuff. Last week with Elena, we saw why it is important to do congestion control in the internet. Today we will see how it is done. So why is it important to do congestion control in the internet? What happens if we don't do congestion control? There might be congestion collapse. How do you define congestion collapse? Sources send more than the bottlenecks can accept. It's true, but it's not sufficient. Congestion collapse is worse than that. Remember what we saw last week is that congestion collapse is a cascading effect where when the network is deeply congested, the usefulness, the useful throughput of the network is much, much less when sources send a lot than if they send less. So it's a non-monotonic property of the network, which is a similar symptom you see on the road systems. For example, the throughput of a highway when it is congested is much less in terms of cars per hour that can flow through a road segment than when it is not congested. And congestion collapse occurred in the internet when there was no congestion control in the early days of the internet, and the symptom was a catastrophically low throughput of all TCP connections, where everybody was perceiving very, very low throughput. With congestion control, we will avoid congestion collapse, and we will have a number of other goodies. In particular, we try to aim at sharing the bottlenecks fairly between all the competing sources. Of course, if you have a network where there is no congestion risk at all, for example, you are connecting a few temperature sensors to a temperature controller over a network that is at 100 megabit per second, and each of the sensors sends one reading every second, for example, then the traffic is so small that there will never be any congestion. For such systems, they can live without congestion control. So if the internet would be so over-dimensioned that we can guarantee that there is never any congestion anywhere, we would not need to bother. But of course, this is not the case. There is congestion, in particular when we use video, large volume transfers that may have to, might require more bandwidth than is available, and then the problem is how to share the bottlenecks. The good news is that it's simple in TCP. The bad news is that there's lots of TCPs. So we will try to go through these jungles of methods that are being used today. So we'll start with TCP Reno, or TCP New Reno, sometimes also called. So the first thing to realize is that congestion control in the internet today is on the shoulders of TCP. It's considered to be a transport layer function. Originally, it was not. And in fact, in the first week, when I introduced you to the layering model of TCP-IP, I did not mention that a function of the transport layer is to control the amount of traffic that goes into the network. That came as an afterthought. Initially, the goal of transport layer is to be an interface between applications that see blocks of data and a network that sees packets. That's the initial goal of transport. When congestion collapse occurred in the internet, the decision of the designers of the internet at that time was to do something in the end systems. And if you do it in the end systems, rather than inside the network, the natural place to put it is in the transport layer. And in fact, only TCP. Why only TCP? Because it's assumed that UDP sources are not sending a lot of traffic. At least that was the thinking when this was developed. UDP would be for sending a request to a DNS server. You don't do a massive transfer of the entire database of a DNS server using UDP. If you do this, you use TCP. So that's why it is in TCP. Of course, there might be UDP sources today that use large volume of traffic. This might be the case for some Skype type of applications. When you do real-time video or real-time audio, then you naturally use UDP for reasons we have seen before, because you're not happy with repeating lost packets. If you do this, you will need to do congestion control in your UDP application. We'll talk about it a bit later. So TCP now is overloaded with a supplementary function, which is to adjust its sending rate to achieve some kind of fairness in the internet. Now TCP, at least the current version of TCP, does not adjust a rate exactly. TCP has another mechanism to control the amount of data that is sent. It is a window. So what TCP does in terms of congestion control is to add another variable called the congestion window that is adapted to the state of the perceived state of the internet, and that limits the sliding window. So the sliding window is limited by the window advertisement received from the other end. In addition, it is also limited by a state variable called the congestion window. So we'll see in detail how the congestion window works. We will start first with the historic version of TCP called TCP Reno with SAC, and what is mostly present in the internet in terms of TCP is more probably TCP cubic. That is an elaboration of this that we will discuss a bit later. Then we'll talk about also newer versions that are emerging, data center TCP and TCP BBR. So let's talk of the historical version, TCP Reno. It uses exactly what we have seen last week, additive increase, multiplicative decrease, plus slow start being a mechanism to go quickly into the stationary window, because if we don't do that, it might take a long time if you start late and other connections are already open. So as I mentioned, the usable window of TCP is the minimum of the offered window obtained by the window advertisement and the congestion window. Right? AIMD is interpreted in the following sense. The positive feedback is when you receive acknowledgement for data. We have seen that AIMD uses a thought model where we receive from the other destination a bit of information. That was the DEC bit originally. Now in TCP, they could have done this when there was congestion collapse. They could have decided, let's add a bit somewhere and let's call it the congestion bit. We will see that it occurred, but a bit later, unfortunately. So they decided to be smart in some sense and say, we don't need a bit because we can detect losses by seeing whether there is an ACK or whether a packet is lost. So a positive signal is when I receive an ACK. A negative signal is when I detect a loss. When I receive positive feedback, I do additive increase. We'll see in detail, but roughly speaking, it means that we add one full-size packet, MSS, maximum segment size, and we do that once per RTT. The effect is to increase one MSS per RTT to the rate. The multiplicative decrease in this version of TCP is by 0.5. You divide the congestion window by 2. Slow start, which is a multiplicative increase, exponential increase, uses a growth factor of 2. Right. So let's see how in practice this is done. The additive increase is done when, in different ways, depending on which version of TCP Reno, in fact, but this is the most common version we see in Linux. Whenever an ACK is received, we do this formula. We have a state variable, which is the congestion window, and we increment it by this quantity, which is MSS to the square divided by the size of the congestion window. Seems a bit weird as a formula, but if you rescale the formula the formula is in bytes. This is in line with all the counting of TCP, which is in bytes. If you count in packets and assume all packets are of the same size equal to MSS, this means that the congestion window counted in packets is increased by 1 over the congestion window. If you rescale everything, you need to divide everything by MSS, and that gives exactly this formula. Which means what? It means whenever I receive one ACK, I add 1 over the size of the congestion window. Here is a small animation or simulation. We send 1 packet. Assume the congestion window would be 1 at the beginning. When I receive an ACK, then I add 1 over 1, which makes it 2. When I receive a second ACK, I add 1 over 2, which makes it 2.5. When I receive another ACK, I add 1 over 2.5, which makes it 2.9, etc. So this is what some implementations do, and it is a computer science approximation of saying if when I receive a full window, I add 1. Right? Of course, it's a bit less because here what I add is 1 over something that is diminishing. Other implementations do exactly this. So other implementations do wait until the congestion window are ACKed and then increment the congestion window by 1 packet. That's an alternative implementation, and the intention of this formula was to approximate this. So this is a bit less than additive increase. A bit less because we wait, even if we do this, we wait for a full congestion window to be received, which takes a little more than 1 round-trip time. It takes 1 round-trip time plus the time to transmit a full congestion window. But this is what TCP Reno is doing, and it is therefore approximately doing additive increase, a bit less than additive increase, but it's approximately doing an additive increase of 1 packet per of the window, and adding 1 packet to the window has the same effect as adding 1 MSS over RTT to the rate. The multiplicative decrease is done by simply reducing the window by 0.5, and we will see that there is a concept of slow start threshold that we'll discuss in a second. The multiplicative increase, which is during slow start, is easier to understand. It adds 1 packet for every acknowledgement received, which will have the effect that if you start with 1, when you receive 1 packet, the window is 2. Then when you receive the first acknowledgement, the window becomes 3, and when you receive the second, it becomes 4. So you effectively double the window size whenever you have received a full window, which is the approximation of multiplicative increase. So we see that by keeping counters on the congestion window, we are approximately simulating additive increase, multiplicative decrease. So this is a trace, a fake trace over time of how the window size evolves as a function of time here. So when, and assume I'm ignoring slow start here at the beginning. So as long as I receive positive acknowledgements, the size of the window increases, roughly speaking, linearly. Then when there is a loss, we halve the window. We divide the window by 2. But in fact, when there is a loss detected by timeout, there is a small complexity. When a loss is detected by timeout, which in modern versions of TCP, even in TCP Reno, is considered an exceptional case. We expect that the other heuristics we have seen with selective acknowledgements and fast retransmit are able to detect losses. And if we detect a loss not by those mechanisms, but by timeout, the belief is that that means that something really bad has happened. Because if there would be an isolated loss, I would have detected by fast retransmit. We've seen that this is not always true, in particular if this is a tail loss, if this is one of the last packets that is being lost. But in TCP-Reno, we don't go into so many subtleties. So if we detect a loss by timeout, we assume that's a hard loss and the state of the network is bad. Perhaps because there was considerable congestion that we have not yet detected, or there was a change somewhere in the route or in the server. So if there is a change, we go into slow start. The idea of slow start is to start from 0 and then increase quickly until you perceive a loss. So this is exactly what we do here. When there is a loss detected by timeout, the window goes to not 0, but goes to 1 or 2. Then it increases very fast. In fact, this increases exponentially. And it increases until we obtain the value which is half the value we had before the loss. So this value is stored into a variable which is called practically by everybody the slow start threshold. So the slow start threshold is the target value that we aim at reaching in slow start. And from this point, we continue growing almost linearly until there is another loss. So this is how TCP will work with those two mechanisms that I have shown. So we see that additive increase occurs continuously and multiplicative increase occurs at discrete points in time when there is a loss. The term that is used for this phase is called congestion avoidance for whatever reason. Now, when there is a loss detected, you expect most of the times the loss are detected by fast retransmit. When you do fast retransmit, you should not go into slow start. So what would the natural thing be? The natural thing would be if you detect a packet loss with fast retransmit, you apply multiplicative decrease, so you divide the window by 2. That would be the natural thing to do. And if TCP would control the rate and not the window, this is what TCP would do. But TCP is using a window. Now, a window is only an indirect way of controlling a rate, and there are side effects of controlling the window. One of the side effects of the window is that if a packet is lost, then this blocks the window. Because the principle of the sliding window is you can send so many bytes starting from everything that has been acknowledged in sequence. So if you lose one packet, then you might be blocked. You might be unable to continue sending. So as soon as there is a loss, there is in fact very often a phenomenon that is hard to control, which reduces the rate automatically. By how much it reduces the rate, we don't know. It depends where the loss is in the current window. But there is a risk that if we simply divide the window by 2, that we block the sender that is unable to continue sending, which is not what we wanted. We wanted to reduce the speed of the sender, not blocking it. If we block it, that means we set the speed to 0. So this is the subtlety that explains why we need to be a bit smarter. So the smarter thing would be to do a rate control. Put a packet counter that counts how many bytes are sent every second and controls this rate. But this is not what is done in TCP-Reno. In TCP-Reno, we keep controlling things by the window. So what we do is we use a slow start threshold, the target window, which is divided by 2, but we temporarily allow the congestion window to increase, in fact, to increase very fast until the loss is repaired. When the loss that triggered this phase is repaired, then we get to the target window. This is an attempt to mitigate the side effect that was given below. So here is the pseudocode of fast recovery. Whenever a loss is detected by duplicate acts, for example 3, then the slow start threshold, which is not really a slow start, but the target window is 0.5, the current size of the window, which we make sure is never less than 2 MSS. And then we increase exponentially fast the congestion window, make sure so it doesn't get too large. And, no, sorry, we start with this, and then here is the exponential increase. Like in slow start, we increase the window, but starting from this value until the loss is repaired. So here is a small cartoon. So we send a packet, the congestion window and the slow start threshold are both equal, so we're in congestion avoidance. So the window will increase by 1 over the congestion window for every acknowledgement received. We send a packet here, and the packet is lost. So when we receive this acknowledgement, which is the acknowledgement for this packet, we increase the congestion window by 1 over the window size, which gives this. And then, when we receive further acknowledgement, 1, 2, 3, here we detect that we are in fast retransmit. So here is the detection of the loss. Here we did nothing because those are acknowledgements that are not advancing the acknowledgement field, so they do not have an effect on the congestion window. Here we apply the algorithm called fast recovery that accompanies fast retransmit, which is a heuristic that says we have the congestion window, so in round numbers it's 400 approximately. We start with this plus 3 packets. Here the maximum segment size is 100, which is very atypical, but it's just for the simplicity of this cartoon. So we start from this value, and then for every acknowledgement we will receive, we add 1 packet, 800, 900, 1000, until the packet, the loss that had triggered this is repaired, which we will observe here. Here when we receive this acknowledgement, 900 because we are repairing the loss of the packet 200, but we had received a large number of other packets here. Then when we receive this, we exit fast retransmit with a congestion window, which is the slow start threshold, so the 407, which is half of the value that we had here. So from 6 to 20, we have an inflated congestion window, the goal of which is to allow this source to continue transmitting new packets instead of being blocked as it would be if we would simply set the congestion window to 800, for example, then it would be blocked here. It would not be able to send packets at time 14 and 17. For example, at time 20, question to you, what will this source be able to send? I close the poll in 5 seconds. And I have a majority of D, which, if I am not wrong, is wrong. Of course, it's hard to put yourself into the mind of a computer running TCP, but let's try. Here at time 20, we have a congestion window of 407. So there's a dramatic reduction from before. Now, what did this source do? It has an acknowledgement of 900. That means the last packet that is acknowledged is this one. This one has not yet been acknowledged. It will come later, but it's not yet been acknowledged. And the window is 4 in terms of full-size packet. This TCP source can send 4 packets in the window, but it has sent 1 already, which is this one. So it can now send 3 new packets. Perhaps more if an acknowledgement comes in between, which hopefully will be the case, but if it has a lot of available processing power to generate 3 packets, it can do it here. So the correct answer is 3 here. The take-home message is controlling a rate with a window is, of course, something that's a bit tricky, and fast recovery is a heuristic that hopes to do a good job, and probably it's true as long as this phase, which we don't really understand what happens in this phase, is not too long. So if those happens rarely, and if this time is not very large, then we can say that TCP Reno does additive increase, multiplicative decrease. Another question. I close in 5 seconds. Last opportunity to have your voice into the system. Now the vast majority says B, which is good and correct. Well, the TCP source doesn't know that there is a loss due to channel errors for lots of reasons. One of the reasons is that the TCP source might not be on the Wi-Fi network. Perhaps the TCP source is the server somewhere in the world that's sending to you. You are on Wi-Fi, but the source is somewhere else. So that source might not see that there's an error due to Wi-Fi. Second is that even if it would be on the machine, there is no link between Wi-Fi and TCP, at least in what we have seen. One could imagine making that link, but today there is not. So it doesn't know, right? So the answer is unfortunately B, which is unfortunate. It means whenever there's a loss, it's interpreted as congestion, right? So that means when you're downloading content from a faraway server, you're competing with others. Whenever there is a loss, your competition is your controller, TCP, thinks there is congestion, so will reduce the rate at which you receive data. If it's a loss due to not congestion, but due to transmission errors, of course that's a bad idea. You're just penalizing you. This is one of the reasons file transfers sometimes don't work well when you're on cellular or wireless networks, is that you might go into slow start many times because of local transmission errors, not because the server is saturated somewhere at the other end of the world. This is why there are sometimes TCP proxies, we'll talk about that a bit towards the end of the course, to try to mitigate this problem. So this is how we can view the congestion status of a TCP Reno connection. In addition to all the bells and whistles of TCP, it does this thing. It is in one of those 3 phases and in addition to being in one of these phases, it needs to keep values of slow start threshold and the congestion window. What does this bring into a network? The goal of this stuff is to provide some allocation of rates that is Pareto efficient and fair in some sense. So what does TCP Reno do? Well, what we have seen last week is that additive increase, multiplicative decrease provides a form of fairness that's given by the blue line here, which is given by some formula with logarithms, which is a utility fairness that as a first approximation is close to proportional fairness, but a bit skewed more towards max-min fairness. Well, TCP Reno is practically the same. It's not exactly the same because we've seen there are small subtle differences in it's not exactly doing additive increase, multiplicative decrease. And under highly simplifying assumptions, we can derive a utility formula. So the utility is this beautiful arctangent formula that gives the utility that TCP assigns to source I having rate xi. So if you have a network with a number of large flows that last for some significant amount of time, then everything happens as if there would be a central controller that is assigning to all TCP connections a rate such that it maximizes this utility, subject, of course, to the feasibility being derived by the constraints on the link capacities, on the server capacity, and on your host capacity. So that's the first good news. It means TCP does the job that we know from theory we have to do. We have to achieve some Pareto efficiency and fairness in a network, and TCP is doing something like this. There is a small bug, though, is that this has a dependency on the RTT. Right? So if we ignore the RTT, we can say for sources that have the same RTT, the fairness of TCP is something between proportional fairness and max mean fairness. Since both are good and we don't know which one to choose, being in between is fine. However, we can ask the question, how does it depend on the round trip time? Well, it's not so obvious because here there's 1 over tau and here there's tau, but the arctangent is a concave function, so the 1 over tau dominates here, and we can verify this by here I'm plotting the utility, this formula, for a fixed x as a function of tau. And we see that it's a decreasing function of tau, which means that the utility that TCP assigns to you is a decreasing function of your round trip time. So what does it mean? If you have a large round trip time, the utility assigned to you is less than if I have a short round trip time. So imagine there is a social planner that gives the rates to everybody. If I have more utility, I am more important because I have a small round trip time, I will get more of the bottleneck, of the limiting capacities. Right? If my utility, if the factor in front of my utility for a given rate is twice as much, it is as if I would be 2 flows for me. So I will receive the same thing that if I would be 2. Right? So flows that have a small RTT are first-class customers in the internet. Flows that have a large RTT are second or third-class customers. So they receive less. Yes? It is not necessarily bad. Can you expand on that? Oh, I don't know. What do you think?
Well, in some cases, maybe if we have larger round trip time, maybe more failures can occur. So maybe it's nicer to transmit all the packets faster to someone who might be closer, have shorter round trip time, and maybe less chance of failure between. So we might finish that transmission and close that connection and maybe have more than for the others.
So you're saying if we have a large round trip time, it would be better to get a higher rate than if we have a smaller one, right? But that's the opposite that TCP will do. Okay. TCP will give less to the TCP penalizes connections that have a large round trip time, right? So is that desirable? Well, let's see a concrete example here. Here are 2 connections that are accessing a bottleneck. The bottleneck is 1 megabit per second here, and S1 is transferring data to a server. S2 is also, and here they have a high-speed link, but one is 20 millisecond round, is such that the end-to-end round trip time is 20, this is 20 millisecond. If we ignore processing time, we can think that the end-to-end round trip time for this guy is 20 plus 10 times 2, 60. And for this guy is 70 times 2, 140 milliseconds. What will happen to those 2 sources? I close the poll in 5 seconds. And of course, the answer is A. As for the reasons we have discussed before, and this is, for example, if we plot as a function of time the amount of data that is received by the destination of S1, so the ax that S1 has received, we're likely to see something like this, that S1 will have a rate considerably larger than S2. Right? So is it a good thing? Well, in some sense, yes. Because if you have a large round trip time, that means probably you're using more hops in the network. And we say that the principle of proportional fairness, it's you should not receive the same rate if you're using more hops, and if there are congestion on multiple hops, than someone who's using fewer hops. That's what proportional fairness does. So we expect TCP to do something like this. But TCP is going beyond this. If we have 2 flows that are exactly using the same bottlenecks, then the ones with the larger RTT are penalized. This is undesirable. It's a bug. It's not a feature. It's a bug of TCP. Sometimes they are confused. You read some papers that say, yeah, but it's fine because the It's proportional fairness. No, it's not proportional fairness. If we would find a way to remove this bias, flows that are using lots of congested resource would receive less, but not because they have a large RTT, but because they're using many resources that are congested. Right. We can put the finger on the cause of this, is that the additive increase is 1 packet per RTT, right? So if your RTT is very large, you increase less fast than if your RTT is small. So we're doing additive increase, multiplicative decrease, but the amount by which we increase is larger than when we have a small RTT. So that's the reason. TCP Reno has been for many years really the model of how congestion control should be behaving in the internet, because that's the first stable solution that solves the congestion control and congestion collapse issues. Therefore, a lot of attention has been given to understanding it exactly, and in particular, there is this very useful formula, which we call a loss throughput formula, that says how the loss probability relates to the throughput experienced by TCP connection. It says that the throughput is proportional to the packet size, because TCP congestion control reasons in terms of packet sizes, which is a bit weird. We see there is an orthogonality in TCP, a split brain, if we want. On one hand, TCP sees streams of bytes, but when people reasoned about congestion control, they thought in terms of packets, not in streams of bytes. So we find this split here. And as an effect, the throughput that you get depends on the packet size. If you have a larger packet size, you will get larger throughput with the mechanisms we have seen. 1 over RTT is the bias towards the RTT we have mentioned. A magic constant, 122, which is square root of 1.5, divided by square root of the loss probability. This is a highly stylized formula. You can find its derivations in the written lecture notes that I post on the site. They are based on analyzing the increase and decrease system of TCP, ignoring all the embarrassing details. We ignore slow start and fast recovery. We assume they have no impact. And this is also assuming that the loss probability is constant. So loss events occur exactly like in the model we saw before. Whenever the rate becomes too large, then we hit a loss. Nonetheless, it has been verified that it is a valid coarse approximation that helps us understand how TCP works. Right? For example, if we go back to the example we studied a few minutes ago, we said S1 will get more than S2. Can we go beyond and we say, what is the ratio of the throughputs that S1 and S2 will get? Are we able to say something about this? I close in 5 seconds. And the correct answer is C, which is the majority, simply because the round-trip times are inversely proportional to the throughput you will get, and the round-trip times are proportional to 3, 20 plus 10, and 7. So the throughputs are in inverse proportion. So this one and this one will be in the proportions of 3 and 7, which gives this ratio here. If you know that the only thing that this link is carrying is those two flows, you could even conclude approximately what is the rate that those guys will get. Theta 1 and theta 2 are in this proportion, and the sum of the two will be close to 1 megabit per second, because we know TCP is Pareto efficient. It's implementing a form of fairness. So the minus the overheads, minus a few epsilons, what we should get here is 1 megabit per second split into proportions of 3 and 7, which means that this guy should come close to 700 kilobit per second, and this one 300 kilobit per second. Right. So we can guess what the values will be. In the lab, we will ask you to verify this. Depending on how things are, sometimes it's accurate, sometimes not, and this is what you will be able to discover. I want to come back to one thing that I described a bit too fast. Here I forgot to mention what is the red stars here. This is the formula that gives the fairness of TCP, and in blue is the formula that gives the fairness of additive increase, multiplicative decrease. The formulas are different, but you see that in practice, if you normalize them by the same quantity, 1, they are practically undistinguishable. So they are the same. Voila, that's all we will do before the break. That's with 1 minute of advance, which is quite unusual. But, and the reason for giving you 1 minute is that you should now do the evaluation if you have not done it already. We're ready to restart. We've seen TCP new Reno or TCP Reno, which are from these viewpoints the same, which are the basis, I would say, for the accepted congestion control in the internet. Now it has a number of shortcomings. Can you think of some? It's better than not doing congestion control. Still, there might be a number of issues. Can you imagine some? Well, we've seen one. It reacts to losses, even if they are not congestion. Right? There are other, more subtle ones. One of them is, what should the correct size of buffers be? If now you're designing a router or a bridge, you will put buffers of which size? Well, probably as you can put as much as is reasonable economically. Right? So 30 years ago, the buffers were small, in the orders of hundreds of kbytes. Now they are huge, gigabytes. Right? What happens if you have a huge buffer with TCP? Assume you have a connection that you have a link that has a huge buffer in front, and the link capacity is not sufficient for all the flows that are using the link. So what will happen with TCP? The flows will start feeding the buffer. Now you have 1,000 flows, and the buffer keeps the packet. So the 1,000 flows are not able to be pumped out at the speed of the line. So some of the data will be stored in the buffer, right? Which is good. Instead of losing them, you will store them in the buffer. But if the buffer is very large, what happens is there is no loss. So the sources don't see that there is a problem. They continue sending at the full rate. And it's only when the buffer is completely full that you will have a loss, and sources will say, oh, now I have to do multiplicative decrease, reduce my rate, and stop sending. Or adapt the rate. But this adaptation will take a time that may be long if the buffer is very large. Perhaps it will take seconds. And if the buffer is very large, what will happen? The buffer first fills. Once it is full, it will remain close to full because sources will reduce a bit the rate, which will make some space in the buffer. But it's only when the buffer gets full again that sources will again reduce. So the buffer will oscillate between being very full, if it's huge, and being completely full, at the expense of delay. Then this buffer might add 2, 3, 4 seconds of delay in the path, right? Which is largely inefficient. There is no benefit of the buffer being huge and full. The buffer just needs to be large enough to compensate for the statistical multiplexing, make sure we don't drop packets unnecessarily. But once the buffer has 1 packet of every flow, for example, then there's no point continuing buffering them. It's better to give an early signal to the sources. That's one of the problems, and we will see how it is addressed by mechanisms which are not cubic, but others that come next. Cubic is addressing another problem. The other problem is explained in this slide here. It is in the case where you have a very, very large bandwidth delay product, which can occur in what is called long fat networks, elephants. If you have, for example, a very long network that has a latency which is not negligible, 100 milliseconds, for example, here, so you don't have this buffer bloating problem that I mentioned before. Assume you have found a way to avoid it, but you still have 100 milliseconds because you're transferring from across the ocean, for example. But assume you have a large throughput, 10 gigabits per second for one TCP connection. Of course, that's not you and me streaming from YouTube, but that might be Google doing a copy from one data center to another one. A huge database file is being backed up from a data center in Ireland to a data center in India. And you want this to happen at gigabits per second. Right. Then this is a cartoon taken from this paper with those, I assume the MSS is huge. This is called jumbo packets, 12,000 bytes, which is larger than the normal IP packet size. But in some conditions, if you have very high-speed links, sometimes you allow packet sizes that are larger. This is done in those kind of environments where you want large, very, very large throughput. Then this is also used at CERN, for example, when in Geneva, when they do high-energy physics experiments, they create lots of collisions, and then you observe whether something happens or not. So you have huge terabytes of zeros and ones, and you are constantly transferring them from a point where you've measured to a point where you want to store. If you use TCP, the standard TCP for that, this is what TCP will do. In fact, this is the normal behavior of TCP. In an ideal case where things are not random but very, very smooth, TCP increases the window size until it hits the capacity, then it sees a loss, it reduces by 1/2, and then it increases it. In fact, it's by analyzing this diagram that we can have the loss throughput formula. But if we look at the numbers for here, we see that the increase time here for those jumbo packets and this relatively modest round-trip time, but if we are at gigabits per second, it's 1.4 hours, the time to climb here. So this increased time is too large, or you could say the decrease is too large, whatever. But the approach that TCP Cubic is doing is observing that, oh, in these cases, if I want to have very, very, very large throughputs for the cases where the round-trip time is large, then I need to increase faster here. So that is what TCP Cubic is doing. So how does it do it? It keeps some of the things of TCP Reno identical. It keeps the same slow start, same congestion avoidance. That means whenever there is a loss, we increase by 1 MSS per round-trip time. But when there is a loss, the multiplicative decrease is less severe, is by 0.7 instead of 0.5. And during congestion avoidance, when we, sorry, I said we keep the phases, but the details of the phase are different. During congestion avoidance, we do what is called a cubic increase. So why cubic? It's literally because of the x to the cube function. Right? If you plot the function x to the cube, you see something like this here, which is a function that increases in a concave way. That means it increases less and less fast until it reaches 0, in which case it starts increasing in a convex way, faster and faster. In details, the window size of TCP Reno is incremented by 1 MSS over every round-trip time. Instead, the window size of cubic is incremented by something that is based on a concept of time. So we compute W of t given by this formula, which is a cubic function in blue here. It's a cubic function that has, at some time, capital K, it reaches this inflection point, and this capital K is computed such that at time 0 here, which is when we are now, when we detect a loss and we enter this phase, we have exactly 0.7, the window size that was before. So we replace what TCP Reno is doing. When there is a loss, slow start threshold is equal to 0.5. Here, slow start threshold, which is called W of 0, is equal to 0.7 here. Sorry, the slow start threshold is W max, but here we start with 0.7. And then we will increase, instead of increasing linearly like we do in congestion in TCP Reno, we'll increase with this formula, which is a bit contorted, but this is how it is done. This 0.4 here is one magic parameter that was based on evaluating a number of cases. They've tried 0.04, 0.4, 4, etc., and they found that this is a good value. So the window increases. So what will happen if we are in a stationary regime where W max was close to the good value? Then we will do this. So we will have a slow increase. In fact, a slower increase perhaps than TCP Reno is less than linear. But if the W max that we had here was not the stationary value, was very small compared to what we could reach because we have a very high speed link, then once we have obtained this, we will grow very fast here. So it combines the cautious part of TCP Reno with something that will explore very fast, a kind of slow start, if you want, when we pass this. So this is what I had explained. If we compare this is the additive increase we would have in Reno, not exactly, because we've seen it's a bit less than additive, but approximately this is what we would have when we have a round trip time of 100 milliseconds. If the round trip time is larger, then we see that cubic will be much faster, which is what is desired. Cubic is targeting large bandwidth delay products. That includes in particular when the round trip time is large. Here. There is an additional thing that if we take literally what is said here, you could find cases where the blue curve is less than the Reno curve. So what Cubic wants is to be slow and safe here in this region, but not too slow. And since I mentioned this fact already, TCP Reno has been considered by the internet community as the golden standard of congestion control. That's the gauge against which you want to compare yourself. So you don't want to be slower than TCP Reno. You don't want your congestion control algorithm to perform less than that. You don't want to get more than TCP Reno if the conditions are the same. You want to get more if the bandwidth delay product is much larger, but not otherwise. So to achieve this, they have added another mechanism which says that the Cubic's window is in fact not the WT that we gave before, but it's the max of two things. The WT given by the Cubic formula, and another formula which is, we could think of it as the window we would have with TCP Reno. But in fact it's not the same, because TCP Reno does a decrease of 50% here, whereas Cubic does a decrease of 30%. So to be consistent with that, the authors of Cubic have found this cute thing, which considers, well, let's do the following. Let's compare a hypothetical version of TCP Reno, which would do a decrease of 0.7, not a decrease by 0.5, but a decrease by 0.7. Of course, if we do that, we are violating the golden standard. We are more aggressive than TCP Reno. So we will compensate that by having an additive increase which is less, such that the throughput formula is the same. So the throughput formula, if you remember, we have seen before the break, the throughput formula that says how much a TCP Reno connection gets given the loss rate. Now you can do the same analysis for a hypothetical TCP Reno that would have a different additive increase and a different multiplicative decrease. So if we take the multiplicative decrease of 0.7, we can have a formula for the loss throughput formula. Using the loss throughput formula, we can compute what the additive increase should be in order to have exactly the same throughput as TCP Reno, if those formulas are exact. And the answer is 0.529. So we could do a different TCP Reno that would decrease the window not by 50%, but by 30%, and that would increase by every round trip time, not by 1 MSS, but by 0.529 MSS. In average, they would get the same throughput, both. This TCP Reno, by the way, would be better. It would, because the window would oscillate less, so it would not have such a dramatic reduction by 50%. Nobody has done it, this TCP Reno, other than as a thought experiment. Here they say, we take as a gauge this version of TCP Reno, and we want to do at least as much as them, which gives this formula here, which guarantees that Cubic's throughput is always as large as Reno's throughput, with equality when the RTT is small. Which gives the following throughput formula for Cubic. Cubic also has its throughput, loss throughput formula. The blue one is the loss throughput formula you obtain with Cubic if you would strictly take the window increase given by the Cubic formula, the formula that's given here. If you use this, you obtain this blue formula, but because you do not exactly this, but depending on the conditions, you do Cubic or modified Reno, which would have this formula, which is the same as modified Reno. Now, what has disappeared is the MSS term. So in this Cubic presentation, all the units of data is the MSS. So MSS is 1, if you want. So that means that Cubic will get the most of the two, which gives this loss throughput formula for Cubic as a function of the loss rate and the round trip time here. So this is Cubic. Nobody has really studied more than that, but it's deployed. So on most servers today, which means most servers are using Linux, then they probably, most of them use Cubic to transfer data. So when we get to a web server somewhere and we get the information back, at least at the source, at the sender side, on the server side, the congestion control is done by Cubic. Remember, congestion control is only how you compute the congestion window in TCP. All the rest of TCP is not affected by this. So this is Cubic, and Cubic is addressing the problem of having very large throughput if the bit rate is very large, but also the round trip time is very large. Now let's go back to the problem I mentioned before. Remember, before I said there is a problem if the buffer is too large. So in some sense, buffer size is like everything in life. It's like eating. If you don't eat enough, then you get sick. If you eat too much, you also get sick. Right? If you watch too much TV, it's the same, etc. Every good thing is good if it's in the right amount. Buffer is the same. If the buffer is too small, so here this is taken from this paper here that's advocating BBR. It is plotting as a function of time what happens to sources that are trying to push data into a link. And it's showing the delivery rate, so what I call the throughput. And on this axis is showing how the round trip time evolves. Right? So if you have a very, very large buffer, the example I gave before. So what will happen as you start sending data, you first increase your window, you fill the buffer, and then the rate at which you deliver data does not increase, even though your window is increasing and you're sending more and more data into the network. But the rate at which the destination is receiving data is not increasing because it's limited by the network, which is called here in this thought model. The network is just one bottleneck link here. But when you're doing that, you're filling the buffer. Therefore, the delay increases here. And this symptom, which is called the buffer bloat, the buffer will be very full with no value for anybody. In fact, with a negative value because the round trip time will increase. This will be bad in particular if you have, now you're saying if you're transferring your terabytes of data from one data center to the next, probably the increased buffer here, the delay here, might not be so dramatic. But if you have interactive flows that are competing with you, that are using also the same bottleneck, the interactive flows will suffer a lot from this buffer being full. An interactive flow is when you do a Skype session, or simply when you do a Google search or any kind of search. You send one query using TCP. Now, if this TCP goes into the buffer that is very full, or DNS query somewhere, if the buffer is very full, you'll have large delay for everybody. So ideally, you would like to operate here. You would like to find a mechanism that has the buffer just as full as it needs to be, but not more. Well, in fact, we have seen a solution for that. It's when last week with Elena, when we saw the DEC bit, or this feedback mechanism, if we can feed to the source an indication of congestion before the buffer is full, then we can achieve this. And that exists in the internet in the name of explicit congestion notification. Here. So the idea is that if you're running this buffer, as soon as the buffer gets more full than, let's say, 10–20%, you start with a small probability sending negative feedback for the sources so that they know they should not go above here. If they don't, or if there is due to randomness in things, you still have some free buffer to store and absorb fluctuations, but you start giving some feedback to the sources here. So how is it done with TCP and IP? Well, here I'm showing a server that's sending data to a receiver, and I have a router here with, in red, a link that is saturated, which is the bottleneck. So how do we get this one bit of feedback back to the source? Here the problem is, this is a network layer problem. It is this link that is saturated. How do we pass this information to the source? Now, congestion control is in TCP, in the internet. This we won't change. So we need a mechanism to go from the network problem to the TCP source. So this solution must involve both the TCP header and the IP packet header. So let's see how. When we use ECN, the TCP header has bits, 3 bits that are reserved for ECN, and the IP header also has 2 bits. So those are one of the bits that we left aside when we studied the IP header. Now it's time to talk about them. So when a TCP packet is sent here, and if it sees a TCP/IP packet is sent, when it sees congestion, when this router sees congestion, as a router, in principle, except if you're a NAT or some special kind of router, your primary job is to look only at the IP header. So if you're congested, you will mark a bit in the IP header. This is the DEC bit idea. So one of these congestion bit here, you will mark it in the header. Then if there are 2 routers congested, it will be marked only once. Congestion will be filled only once. If there's no router congested, nothing will be marked. Now, if you use ECN, the job of TCP and of the operating system here is to make the link between the IP header and TCP. So when the receiver receives a packet that is marked in the IP header, in the reverse direction, it will echo this in the TCP header. So it's called an echo congestion experience. So the TCP header has a bit, which is here marked with this X, this cross, and it will be received at the source. Now the source analyzes the TCP header. One of the bits is marked here. So the source will say, oh, there is congestion, and it will react to congestion as if it would be a loss. It will be exactly the things it would do with TCP Reno if there would be a loss. Here. But of course, if we are smart enough and we mark the packets as soon with an intelligent function that measures congestion here. So congestion can be measured by the level of the buffer, but it can be measured by other things. You can measure the amount of traffic that is flowing on the link, for example. When you're close to 100%, even if the buffer is not full, you know you're close to congestion here. So that's the thing we're missing from the road system. When we poll a road traffic information system. We look at Google Maps to see whether there is congestion on the road. We see the congestion when the buffer is full, so when the roads are blocked. If the roads are 10% below congestion, means they might be congested any time, we get no advanced signal. So here with ECN, the idea is that the routers implement a computation function, some measure of the utilization. One of them is the red function that I will describe in a few minutes, but there are many possibilities. Now, having done this, S will adapt, and therefore, if every source is doing that, then there is a chance that there would never be losses, that we would be reacting to congestion in such a way that the amount of traffic that flows through all links is a bit less than the capacity of the link, therefore there would never be any losses, which is the ultimate goal we would like to reach with a TCP congestion control algorithm. Quick recap question. Can you put the labels on the different phases of this packet trace? I close the poll in 5 seconds. And the majority is right. Here we're doing congestion avoidance, so we're increasing, for example, if we do TCP Reno, we're increasing linearly. If we're doing TCP cubic, we do the cubic stuff. Then when we receive congestion experience, then we decrease the window by 2, by 0, we divide by 2, multiply by 0.5, or by 0.7 if we have a cubic. And of course, we don't go into slow start because there is no loss, there is no timeout. So here we go again into a reduction. And of course, the beauty of that is that if the buffers are large enough, there will be no loss, but also we will not have buffer bloat. The reality of ECN is a bit more complicated because you could cheat, right? Assume you have a server here that's sending data to you, and you are not using ECN at all, or you want to get data faster than a simple. Now, in principle, the servers are done by Google, Apple, people like this. They have no interest in having a congestion control that cheats because the network will be unstable, so their business will not go well. But you, individually, you have an interest in not doing congestion control, right? If you want your data to come faster. The congestion collapse will come if everybody does like you, but if you're alone, it's good for you. That's the tragedy of commons in some sense. Now, with the normal TCP, it's not possible because the congestion control is done by the source, which you don't control. But if there is ECN, there would be an easy way to cheat. What would be this way? Yes?
Never send ECN. Never send feedback.
Yeah, never send, or send a positive feedback, because I showed only the red cross, which is the negative feedback. If you unset the bit, it's positive feedback. So exactly, as you said, if you tweak your Linux PC such that it always says to the server, wonderful, no congestion, then the server will increase its rate with cubic or exponential or even TCP Reno, and will consider that you don't, you're not, there's no problem with you. Of course, if there's lots like you, what will happen? There will eventually be losses. So then we will be back to the normal operation. There will be congestion losses. But if all other people are behaving and you have a large speed link here, there might not be losses because you are a small fraction of the total link capacity and buffer, and you will have an over-proportionate fraction of the bottleneck bandwidth. So you could cheat. This is one possible malicious operation. Whether this is really important or not, I don't know. But this justifies why the bits are a bit complicated. Essentially, to detect this problem, the idea is that an ECN compliant source must check whether the things that you receive are consistent with the fact that, in fact, we don't send only one bit. We have we have 2 bits in the IP header, and in fact we need only one. Is congestion experienced or not? We need also another thing. We need to say whether this TCP connection is reacting to ECN or not. Because if the source is not reacting to ECN, what should a router do? There's no point marking a bit saying this source, please slow down, if this source does not implement ECN, doesn't look at the ECN bit. If that is the case, you should drop the packet. That's the only way you have to instruct the source of reducing the rate. So a router will analyze whether this flow declares that it conforms to ECN, and if not, it will do different things. So we need 1 bit for that. That's why we have 2 bits. But since we have 2 bits, we can use it more intelligently, because in fact we need only to specify 3 things. This flow is not ECN compliant, in which case ignore all the rest, or it is ECN compliant and there is congestion on the path, or it is ECN compliant and there is no congestion. There's only 3 things we can do, but we have 4 possibilities, we have 4 bits. So if there is an empty possibility, somebody will use it, so it is used here. And the idea is that the sources randomly send a 0 or a 1 in one of the bits, which is called ECT, experience ECN capable. I'm not sure what ECT stands for, but it's called the ECT. And the idea is that when the destination echoes the thing, it will do 2 things. It will echo whether there is congestion experience, and it will also give what the XOR of all the bits that were sent here. So if there is no congestion during a train of 10 packets, the destination will receive 10 packets with ECT0 or ECT1. Both ECT means no congestion. But it's the source that decides whether it puts a ECT0 or ECT1. So as a destination, you will receive a number of bits equal to 0, number of bits equal to 1. You do the XOR of it, so you have 0 or 1. And the source remembers exactly what it has sent. So when it will receive this, it of course, in 1 bit, you still have 50% of probability of cheating, but over a large transfer, if this guy is not correctly receiving the things, then it will not be able to echo exactly the number, the correct XOR. So the source will detect that the ECN chain is broken somewhere. In particular, if this guy pretends that all packets were ECT 0 or 1, whereas in reality some were marked congestion experience, when we mark a packet as congestion experience, we lose the bit information, the random bit 0, 1, right? Because there is only ECT0, ECT1, and CE. If congestion experience, you erase this bit of information. This bit of information is a nonce in cryptography, right? It's an additional number you put to make the attack more difficult. So if this guy is malicious, it will have to send a random nonce bit back to the source. And if it does it continuously after a number of blocks of data, the source will decide with large probability that this is not working and this guy is not, so we should not be using ECN. So this is why ECN is a bit complicated, and perhaps also why it is not so widespread here. I mentioned that if you do ECN, you have to compute when to send a bit, when to mark a packet as congestion experience. You don't have that problem when you don't do ECN. You can decide, oh, well, the buffer is full, I drop, okay. One way to do it, as I mentioned, is to have some kind of exponentially weighted moving average of the utilization of the link. Some systems do that. Another thing that was proposed very often is to use so-called red curve. The red curve is a curve that gives, as a function of the average queue size, a packet dropping probability. So it is still based on the queue size, but you don't wait until the queue is full. Before the queue is full, so the queue is full when it is here, so when it is here, probably here, before the queue is full, with some probability, which is not 100%, you drop a packet or you mark it if you use ECN. So if the average queue size is, for example, in this region, with probability 0.5 max P, you will drop the packet here. You will mark the packet as congested. You can use that for ECN. You have to have a function of this kind or another for ECN. But even if you don't use ECN, this is a bit paradoxical, but this is easy to understand with all the things we have discussed. There is value in doing this. So even if you have a very large buffer, the buffer size is this here, there is value in dropping packets before your buffer is full. For exactly the reason we discussed before of avoiding the buffer bloat syndrome. So if you don't have the method of choice to avoid the buffer bloat problem is to use ECN, but a cheap method, if you don't think that servers are using ECN, is to give advanced loss signals by dropping packets even before your buffer is full. This is done with RED. So RED, unfortunately, is not very much deployed in the internet, probably because service providers say we don't want to drop packets if we have space in the buffer. But this is an efficient method. If we don't use ECN and if we don't use RED, then we do what is called tail drop. We drop packets when the buffer is full, and as we have discussed already, this has a number of negative side effects. Right. One next question. I close in 5 seconds. And we expect that there is no congestion there is no packet loss due to congestion in routers. Now the bad news is there's not only routers, there might be loss due to congestion somewhere else. Where could that be? Yes?
The destination, maybe the speed of the button.
At the destination, it could happen, but that would be bad. For that, we do flow control in principle. So in principle, the congestion, the window advertisement of TCP will make sure that doesn't happen at destination, because it's the most stupid thing to do. You've taken the burden of carrying a packet through the entire world, and at the destination, oh, I'm sorry, I don't have space in my mailbox. Then, yes? But it's the same thing. If the server is overloaded, you will not be able to open a TCP connection, or if your TCP connection is open, you will have a small congestion window. Well, there are other animals that behave like routers, but have a different name. They're called bridges, right? They don't see the IP packet, they don't handle the IP packets, but they have input ports, output ports. If the output port is full, there will be congestion. So congestion due to bridges is not fixed here. The assumption is that bridges are in local area network where everything is over dimension. If you have a data center with bridges that are interconnecting the internet to your infrastructure, you should over dimension the bridges so that congestion losses there are rare. So you have 10 or 100 gigabits per second link on your bridge, between your bridges, for example. Other cool stuff, cool or non-cool, we'll see. Data center TCP. Data center TCP is a variant of TCP where, so what is a data center? Data center are the things we access when we watch YouTube, when we use Dropbox, when we send a request to Google. Physically, it's a room with lots of racks of PCs and switches. And most traffic is TCP. So the traffic is a lot between the PCs. When you send a request, there is perhaps TCP between you and the first part in the data center, the portal, and then this sends another request to the backend, and this is typically doing TCP. Now, between the PCs that are in the data centers, the latency is very small. There's lots of bandwidth. There's a huge number of flows with low latency. Those are typically the user queries or the computations of the backend. And once in a while, some jumbo flows, and you have to run all this here. If you have to run a data center, now you do whatever you want. You choose your version of TCP for all the internal flows. The flows to the outside you don't, but for all the internal flows, you can run what you want. So what would you do? What combination would you use? I close the poll in 5 seconds. And we see two modes in the distribution of answers, B and C, which are probably good answers, both. Sorry, B and D. It's a good idea to use ECN. You control everything. So the problem with ECN, if nobody's using it, then if your server supports ECN, but the network drops or ignores ECN, and browsers also ignore it, there's no value. But here in your data center, you can implement ECN everywhere. So you should use ECN and have routers that are more than switches. Now, should you do Reno or Cubic? Well, you probably do Cubic because this is what the Linux servers have. But if you do Reno, there would be probably not much difference because even for jumbo flows, the latencies are so small that there would probably not, will not be going to the Cubic mode. So correct answer is probably this. Now, in fact, what people would do is yet another thing. Cubic is a bit better in some sense that the decrease is smooth, is 0.7 instead of 0.5. You can go even one step further, and if you go one step further, you obtain what is called data center TCP. The idea of data center TCP is to avoid this sawtooth behavior where you go up and down. The only way you have to control TCP is to force it to go down. Right? Okay, I'm being forced to stop. So we'll discuss the end of data center TCP next week. Thank you very much. See you tomorrow.